Okay, we're now on the page looking at area by integration. And because we're dealing with a certain section, usually of a graph or particular area under a curve, we're going to be using what are called limits or definite integrals. So we'll have limits. So let me show you what that means. So the lecturer might say, okay, let's have this as a function, dy dx equals 4x cubed. This is one I've made up beforehand for you to have a look at. Now if we integrate this and find the area, so we need to find the area between x equals nothing and x equals 2. So you say, yes, we can do that. So here's a solution. What we now do is we'll integrate this. So the area is the integral. This is how we write it out. You see, from 0 to 2 of this function, 4x cubed minus 2x plus 6 with respect to x. And here we go. Now, as soon as we start integrating, we change the integral sign to square brackets, which is normally the convention, and then we integrate this out. So raise the power by 1, divide by the power, this becomes x to the 4. Okay, and the 4 divides out and cancels that. Raise the power by 1, divide by the power, this is going to be x squared. 6 goes to 6x, and notice now, we finish this off. At this point, we don't need a constant because we've got the limits. Okay, once you have the limits, you don't need the constant. Now, simply put, we now work out the area by putting the 2 in place of here. So 2 to the 4 is 16, minus 2 squared is 4, plus 12. When you put 0 in there, you get nothing anyway, so there's nothing to take away. So 12 plus 12, this will give you the answer of 24 units squared, whatever they happen to be. So let's have a look now at the one in the book and see where this is going. And the one in the book there, as you see there, integration is also used to find the area under the curve. Find the area between the curve y equals x squared, the x-axis, and the ordinates 2 and 4 for the x. So this is a solution. The area equals the integral between 4 and 2 of the function in y, which is x squared with respect to x. Integrate this, raise the power by 1, divide by the power x cubed over 3, and then simply carefully put your numbers in here. So 4 cubed over 3 minus 2 cubed over 3 equals this. Okay, and if you wanted to go further, you could work that out on your calculator. Now the point that we've brought out here is the fact that no c is needed because we have definite limits within which to work. So this is called a definite integral as opposed to an indefinite integral, which is what we were dealing with beforehand. Now, apart from areas, there are sometimes problems which require a little bit of knowledge about volumes. So let's have a look at the next section. Integration can be used to find the volume of a shape. So here's an example. Simple one says, calculate the volume generated when you rotate the curve y equals x cubed about the x-axis, so it's coming this way, okay, top to bottom, between x equals 0 and x equals 2. So the solution is to draw perhaps a bit of a sketch here to show the situation. Delta x here, if we multiply this by pi r squared, where r, the radius is y, is the actual distance, this is the radius here, then pi r squared multiplied by the thickness of the disk will give us the volume. Okay, so we write this out by saying the volume equals pi, which is a constant anyway, so that comes out. Integrate between the limits, and we were told it was 0 and 2. For the function y equals x cubed. Now, because this is r squared, it has to be y squared. So this is x cubed squared. So we square this becomes x to the 6, raise the power by 1, divide by the power, and it's x to the 7 over 7. Put your numbers in and multiply your final answer by pi, and it'll give you 57.45 units cubed for the volume. Now that comes up sometimes. You may be required to work a particular volume question out. Okay, earlier we said that distance and velocity can be used with integration, and this next section realizes this as well. Previously we noted that the velocity is the change in distance over time, and acceleration is a change in velocity over time. So we can integrate velocity to find distance. We can integrate acceleration to find velocity. So here's a nice little example for you. The examiner gives you this one. The velocity of the body is v equals t squared plus 1 all squared. Find its position at time t when s is 1 and t is 1. So the first thing we need to do is to expand this out carefully. V equals t to the 4 plus 2t squared plus 1. And now we integrate. So we integrate this to find out what s is. So when we integrate this, raise the power by 1, this becomes t to the 5 over 5. This is 2/3 of t cubed, and the 1 becomes t. Notice we must add a c here, all right, because we have no limits, and we can find what c is because the examiner has given us values for s and t. So we put that in. 1 equals, and when you put 1 into t, you get a fifth plus 2/3 plus 1 plus c. Very carefully working this out. For this particular set of data, c has the unique value of minus 13 over 5. If we look at the acceleration at the bottom, a is given as 18 minus 2t. Find its velocity, knowing that v is 20 when t is 0, and find this velocity after 3 seconds. So we integrate acceleration. 18 minus 2t becomes 18t minus t squared plus the c. Putting 20 in place for v when t is nothing, then we find that c equals 20. That's 0, that's 0, and there's only c left, so c equals 20. So the velocity then is 18t minus t squared plus 20, and after 3 seconds, when you put 3 in place of there, v equals 65 meters per second. So this is a typical example where you have to use integration to go back, given either acceleration to get your velocity, or you're given velocity to find the distance.